Hello everyone, welcome to the second video for differentiation applications. Today we'll be covering increasing functions, decreasing functions, and concavity. Increasing functions are functions that only increase, which we can see visually. So for example, we can see that this function increases, this function also always increases, and this function always increases. As such, all three of these functions are considered increasing functions. Now, differentiation gives us a way of mathematically determining if the function is increasing, because if a function only increases, this means that the gradient of the function is always positive. If you look here, the gradient of all these functions, no matter where, are always positive. And if you see where this is going, this means that f prime x is more than 0 for the domain of fx. That's how we use differentiation to mathematically determine if a function is increasing. Likewise, decreasing functions are functions that only decrease. And since the gradient of the function would always be negative, this means that f prime x is less than 0 for the domain of fx. The next thing we're going to learn is concave up and concave down. Let's first look at concave up. The mathematical definition of concave up is that f prime prime x is more than 0 for the domain of fx. In case you forgot, this over here, f double prime x, means that it is the second derivative of fx, which means differentiating fx twice. Graphically, concave up will look like a happy face. Any part of the happy face, including these two left and right parts over here, are also both considered concave up. Likewise, the mathematical definition of concave down will be f prime prime x is less than 0 for the domain of fx. For concave down, the graph will look like a sad face. Again, even if we were to take any part of this sad face, this part over here, or this part over here, the graph is still considered concave down. Now let's look at this graph here. We can visually see that this part on the left is considered concave down because it's in the shape of a sad face. And this part over here on the right is considered concave up because it's part of this happy face. Of course, if we want to find the exact domain where fx is concave up or down, we will need to differentiate twice to find out if f prime prime x is more than 0 or less than 0. Now if you look over here, there's a point where the concavity changes from concave down to concave up. The exact point where this concavity changes is called an inflection point. We will explore more into how to find the inflection point in the next video. Anyways, let's do a question to test our understanding. Show that the function y equals to 8x to the power of 5 minus 1 over x is always increasing for the domain where x is not equals to 0. Now to show this mathematically, we have to use the definition of an increasing function. F prime x is more than 0. Now the first thing we need to do is find the first derivative. So I'm just going to write dy over dx. Of course you can also write f prime x. And we'll find this as 40 x to the power of 4 plus 1 over x squared. Now if you look here, for this domain where x is not equal to 0, can you see that this term over here and this term over here are both always positive? We can say that for all x is not equal to 0, 40 x to the power of 4 has to be more than 0. And also, we know that 1 over x squared has to be more than 0. Because 1 over x squared, and you know that x squared is always a positive number, has to be more than 0. Hence, we know that 40x to the power of 4 plus 1 over x squared has to be more than 0 for all x is not equal to 0. And as such, dy over dx is more than 0. This means that the function is always increasing. Here's the summary sheet for increasing functions, decreasing functions, and concavity. Thank you so much for watching.